Hello, and welcome back to Learning with Lee. In today's episode, we are going to take a look at how formatted strings can be used to output information in C. It's important to note that this is C specific, so it ends up dealing with character pointers for a lot of it, as well as then, in case you want to use C++ strings, you would want to use the C_str method on a particular instance of a string so that you could convert it into a character pointer. For this, we looked at it briefly in the previous episode when we were looking at how to read in and output a double, but in this case here we're going to go through every potential thing you can output using printf. And we're going to go through all the different modifiers on how those can change how you output things. So the important thing to understand about printf is that it only really cares about these percentage signs. You can still use escape characters in here such as \n, or \\/ or anything else like that, similar to normal strings, because those are properties universal to any type of string. However, the percentage sign effectively acts similar to an escape character, but only within the context of printf. Or technically if we wanted to also scanf and the related functions. However, for these set of functions, what they end up doing is they care about this for parsing it, or breaking it down into manageable chunks, and then operating on those chunks independently of each other. However, what really matters is that you're going to have your percentage sign, followed by some set of modifiers, which could be numbers, they can be decimal points, they can be the minus sign or the asterisk. They can even be the hashtag sign, if we head on down to here, and it can also be the plus sign, but it has that, and then it eventually has some character signifying what you want to output. And this might even be two characters, such as in our example yesterday, where we had %lf for outputting a long float, which is just another word for double. So we end up having these to signify that we're going to substitute something in of a particular type. And then what you have to do is you also have to supply the arguments of what you're going to substitute in. And in a future episode, we will eventually get into how this ends up having an arbitrary length of arguments. Because you can pass in as many arguments as you want to, provided that they end up matching with something that has this % sign in front of it, so as it can be substituted in. And you want to make certain that if you have multiple things that get substituted in, they are both in the correct order, and that you have the same number, so as that you don't have more and don't have less in terms of the number of arguments than what you expect to be substituting. For this, the easiest example is just this %s here. That just says, take whatever your string is, and in this case it corresponds to this third argument here, test string, and insert it here, replacing this %s. And you can see down in our output that it happens to take test string and put it between those two pairs of pipes. Then you might notice down here, it looks almost identical down here, or more accurately it does look identical, and that's because what this 5 is doing is it's not doing anything that we can really notice, and that's because it's providing a minimum length. And it becomes more noticeable once we skip down to this line here, and we can see down here how all of a sudden we have this white space here. So if we have a minimum length that's larger than the amount of text that we have in our string, it's going to add on white space, or it's going to add on spaces. And those just happen to be the same as if I started adding in, clicking my spacebar and putting in spaces there. Then you also have the option of having a decimal followed by another number. And the second number tells you the maximum length. And you can see down here how we have just test is what we get out. And the two of these are very useful for just formatting how you want your output to look. And in particular, this decimal followed by this is going to be really useful once we get into things like significant figures and doubles. For strings, it does have some value, but in case we take a look at 15.4 here, which happens to be this line here, you'll see a very important characteristic about it, and that's the order in which these are applied. Your maximum length is applied first, so at first it's going to truncate you down to 4 characters, and then it's going to pad it with spaces up to these 15 characters. So we wind up with these 11 characters, in this case prepended on, to our string. And the important thing about that is that in case it were done in the opposite order, what we would first have is we'd go, okay, we have 15, so we need to do effectively this line right here. And it would create that first, and then we would apply the maximum. And as a result, we'd be left with 4 spaces. we would have lost our entire string, just have gained 4 spaces, which is rather pointless. And I could see certain languages doing it the other way around, because there are situations in which you would want to apply your minimum first. However, it does make sense the way in which C does this, but it is important to remember that it does do this in this order, and that it does operate on this one first, then it operates on your minimum. And one of the things that's important to note here is that this is prepending these spaces. It isn't center aligning it, it isn't left aligning it, it is right aligning it. It is shifting your text so it is on the right-hand side of this buffer of 15 spaces here. However, you can also get on the left-hand side of that buffer by using the minus sign, and that you can see down in this example here, which is just the same as this one here, except that it's left aligned as opposed to right aligned like this one is. So that's how you can end up changing between left and right alignment. Unfortunately, there isn't a way to actually get center align in C. That's something that you would have to do on your own, or use a third-party library to handle for you. Beyond that, you can end up adding on this negative to just a value itself, but similar to if I had done -5 up here, just because of the fact that it doesn't actually adjust the alignment on this one here, it has no visible effect. However, you can actually do something like -S, and it won't give you an error. So it's not something you really in general are ever going to do, because it doesn't make sense to do, because your string is going to take up however much your string takes up. It's not going to have this additional buffer that it can be aligned within. Then we can take a look over here. And what this asterisk is, and you can see over here that we have this negative, and that's how we end up having all of these be left aligned down this list through here. And you can see how it's somewhat useful for creating this little table that I have down here and keeping it orderly and organized. But what this asterisk does is it's a additional substitution. And I could replace, if I want to, on this 15.4, the 15 with an asterisk and the 4 with an asterisk. And what that says is that I need a substitution for both of them. So I could put in 15 and 4 over here, and it would generate the exact same output as had I have had them in here. So what it does is it grabs this width and puts it into here. Now the important thing to note about this is the ordering of the arguments. And that's, you might think, okay, I'm starting with this percentage, so I need the whatever string I happen to correspond to that percentage as the first argument. But that's incorrect. This just tells you to begin looking for substitutions. So it first processes this minus and this asterisk. So first it's going to process this and go, okay, I need to grab that off the list of arguments. And I'm going to get an integer, and in this case here it's width, which is 13. And the reason why you want to do something like this, especially for tables, is that it's a lot cleaner to do that than it is to have something that outputs 13 in every one of these, because if all of a sudden I want to change it to 15, in this case I can just change it in a single spot, whereas the other way, I would have to be changing this guy to 15 and then this guy to 15, and I'd have to do this for every single one of these. So it's much cleaner to be using asterisks to automate this process for you. And it's very useful for when you end up creating your own custom tables. Beyond that, you can end up using that with any of these other modifiers. So you could do the negative sign on, you can do that .4 if I wanted to, in order to limit it to only the first 4 characters, but it still would have that minimum width of 13. I could get rid of this in order to have it be on the right-hand side, but that just happens to be an additional thing to note, and an additional thing you can do with printf is you can use the asterisk in order to get custom integers input as 15 or 4 in order to determine the minimum and maximum. It is important to remember that because these are C strings, you must null terminate your strings. And you can see this example right here where I have this character array error. But because I don't have a null terminating character at the end of it, when I decide to output that character array, it ends up adding on all of these other characters until it hits the equivalent of a null terminating character somewhere in memory. And it's not really a problem with printf, other than the fact that you might be printing out information that you don't want to see, as well as printing out information that quite frankly makes things much uglier for your user, because your user is going to have no idea what to do with this here. All it knows is that you end up messing up something, and they might call customer support and being like, hey, I'm getting this really weird stuff on my display, go fix it. And they won't really know more than that. So that's going to be something to watch out for. it's a much larger error when you end up having to be reading something in, because then you can end up accidentally overwriting information that you already have in memory. It can end up changing how your program operates and potentially even allow hackers to break your program and use it as an exploit in order to gain control of your system or gain control of a customer's system, which you never want to have happen. Then you can also output characters, similar to a string. It just %c. And while this one takes in a character pointer, this one here just takes in a character. So you need to dereference your particular character by either using the subscript notation, or if you want to, I could get rid of that and just use something like the asterisk notation in order to dereference it. And either of those would do the same thing. But it does not expect a pointer, because otherwise it's going to end up messing up how it outputs this, and it won't give you the correct thing. And you see down here how we have t output correctly. And similar to strings, you can use this full set of notation. You can use asterisks. It doesn't really matter, but you can do that with characters. It doesn't make sense to do really a maximum length because a character is only going to have a single character. So the only thing that matters is it 1 or greater, which means your character appears, or is it 0, which means your character doesn't appear, which really doesn't necessarily make sense because at that point you're just outputting a space. I could see times in which you might want to have one of 0, and that happens to be in case, for example, you're lacking information and you're reading from a database, and you want to represent the lack of something by not showing any information at that either text box or some other field, and effectively you end up doing that sort of thing, but we're not going to really be doing that with C. That would be for more of Java or C#, what we end up doing those with. But there could be a reason for it, it just is not something you usually want to do. Then we can output numbers, and numbers are slightly different than strings. We've already gone over LF is effectively for double, as well as we showed that if, for example, I left off this L, it would give me an incorrect value. So there's one really key thing to note. You'll see how long we have for what we assign to double, and the problem is that by default, it will automatically truncate our, and technically it even does a bit of rounding, because if you note it goes to 9.2, and down here it's 9.3, so it rounds to the 6th decimal place. And the way in which this behaves is a bit different. So what we have is we have this 10 here to represent our minimum, and the important thing here is that it might affect us in case, say, I had a whole bunch of numbers, such as over here like this, but in this case here, it's just going to give us spaces. Technically, if I wanted to, I could get rid of those spaces and replace those with zeros by putting a 0 in front of it, so 0, 10. And that would tell me, rather than prepending it with spaces, prepend it with zeros. So in this case here, we would wind up 0, 0, and then 3. However, it is important to note that that does not actually affect our fraction. It doesn't impact anything after the decimal point. For that, we actually need to do whatever's after our decimal point here. In this case here, it'll end up going, okay, I want this to have 10 characters after the decimal point. And note, it's not 10 characters overall. It's saying, I want there to be 10 characters right down here. And that's how you actually get these additional values out of here, though it will still end up rounding for you, because in case you know, it goes 538 up here and 539 down here. So it does round, and it does also truncate for you in case you don't specify to use a larger value. Then there's another problem with outputting doubles and outputting floats, because if this were just a float, it just would be %f. And there's really a couple different things that we'll get into in a little bit. And you'll see down here these %h's, and while you can't really have a short float, if for whatever reason your compiler allowed for that, you would do that using hf. But that's a bit of a side tangent that we can ignore for now. The biggest problem that this has beyond just truncating it for you is that it ends up having problems with very large and very small numbers. And that's that in case I'm trying to output something like Avogadro's number, and I try to do it down here, I'm going to get zeros out. And that's because it converts it into a double. It goes, okay, I'm going to start from 0 and start outputting it. See, the first 6 characters are all zeros, and it's going to just stop there and do the automatic truncation. And because it rounded to 0 at that point, it's as though we don't have anything in there, which is inaccurate because this actually is stored correctly. However, you can't see it by using %lf. We'd have to do something like let's see, 0.23, or really, because that happens to be how many times this is moving to the left, we'd have to do significantly longer than that. We might even want to go up to like 0.30 to get 30 characters out for that, which just is really ugly for in case you have to have this in any form of data that you're reading and is human readable. So you can actually do it in exponential or scientific notation. And for that, you can take a look down here, as well as right here. And the E basically is a variant on float or f, and what E does is it just specifies that I want this float to be represented as an exponent. So it's going to give me something times, or this E represent times 10 to the, in this case here, negative 23, and it's going to give me this correctly. And if I want to, I could still end up including things such as like this 10, and I could do something like 10.10, and it would end up giving me 10 spaces at least, as well as then it would give me 10 spaces after the decimal. So you can still use that with that, and it is very useful for both very large and very small numbers. You can also then output integers, and all the different varieties of integers, so shorts, longs, unsigned integers, but each of these ends up having their own custom different character that goes after the percent sign. The important thing to note is that for shorts, as well as for longs, as you might have already guessed from %lf, as well as I mentioned %hf briefly, for shorts and longs, they actually are just a modifier on another different character that you use here. So for this, I could do D, but I could also do I. And whichever one you use is up to you. For me, I've traditionally used D. It's the one I've seen used the most. It's the one that I first used when I started programming in C. And I can understand that it's a bit confusing just because of the fact that you see D, you think double. It's like, no, doubles are actually LFs because they're a variety of float. And D comes from the term decimal. However, if you want to, you can use I, and it works the exact same way. It's really a matter of whatever standards are for whatever company you end up working for. Then you can also specify things such as I want there to be at least 5 and maximum of 10 characters, similar to how I was doing it with this here. However, there is an important distinction between how this works with integers and how it worked with character strings up here. And that's if we look at this example of our integers here. Because our first one, we just are outputting our integer, and it can output negative numbers. It outputs the sign for you if it is negative. If it's positive, you're going to have to manually do it, but we'll get into that in a second. What you can then do, though, is you can apply something like this a 0.5 and then 0.10. And the 0 just specifies that we want zeros to precede our integer. So you can see that this is the same integer as it is up here. It just has these 4 zeros to fill it out until it has these 10 characters. And the important thing with integers with regards to something like this is that both of these are effectively minimums. In case your maximum, or whatever's after the decimal point, is larger than your minimum, because of the fact that integers don't have any values after a decimal point, it effectively acts as a second minimum. So we still wind up with 10 characters down here, even though our minimum is supposedly 5. So it is a bit weird how it ends up acting on integers as opposed to floats, as well as also then strings. But occasionally this will come up, and occasionally you will have need of using both this side of it and this side of it. Then if you want to, HD, I don't know what the H really stands for in terms of it, but it's for a short decimal. And the reason why they obviously couldn't use S is because S is already used for strings, so they had to grab a different character that they could use. Then if you want to, for any one of these, signify its sign, regardless of whether it's positive or negative, you have to put a plus sign as a modifier in here. So you can see down here how we have initially our short, which is just 1, 2, 3, 4, and that's this line here. And then you see our line below it, where we output it with its sign. And regardless of whether our value was positive or negative, it's going to output that sign. In this case here, it will only output the sign if the sign is negative. Then you have things such as LD or LI for a long integer. Then you have %u, which signifies an unsigned integer, and it ends up outputting it correctly in case we scooch on down a little bit. You can see 567890, which corresponds to up here. And then you can even output varieties of integers, such as octals and hexadecimals. And you can even convert base 10 numbers into those by specifying that you want them output as either octal or hex. And just as a reminder, octal happens to be, and the reason why octal is popular in coding is that it's basically 3 bits. It's base 8. So it's very commonly used when we end up dealing with file permissions and when we end up dealing with a few different things that exist in terms of how things are represented in memory, just because it does represent 3 bits and it's really easy to mathematically figure out what something would be if you limit it to 8 choices like that. And it's relatively easy for conversion. Hexadecimal is base 16, and that happens to mean that it ends up taking up 4 bits, so 1 bit more than octal, because it's twice as large as octal is, base 8 versus base 16. And hex is most commonly used for colors, whether you're using Photoshop, GIMP, or HTML. You'll very often see things such as 0xFF0000. Then, within here, you can see how I have these 0xABC, and the important thing to know about is that basically 0 through 9 are represented normally by digits, but then 10 through 15 are ABCDEF. So that's the major thing to understand about hexadecimal. We're not going to get too much into it at the current time. It just is important to note that you can output it. And you can see down here how we are outputting hexadecimal here. And you can even output, as I mentioned earlier, base 10 numbers such as 567, and then it converts it when it ends up taking it in to an octal number. Because you can see we pass it on the second octal, 567, and it gives us this. And up here you'll note that we precede it with a 0. That's signifying that we want it to be an octal number. So this is octal 777. So you can see down here, it just converts it directly to 777. It doesn't need to end up actually converting it from base 10 to base 8. And down here, all that this little hashtag is signifying is that we want the output to reflect the fact that it is octal. So it's going to prepend on a 0, and you can see that down here, so that you can see that is octal the same way that we can see it within our code here. It might not mean as much to somebody who's not as familiar with programming parlance, but for people who are accustomed to it, it's an easy way to tell when you are dealing with something that's octal. Same thing for hexadecimal, in which we can output something with this 0x here, and it will signify that it's hexadecimal. Otherwise, in case we don't specify this hashtag, it'll just output it in hex without showing us the fact that it actually is in hex. So really, depending on whether you need it to be clear or not, is up to whether or not you end up outputting as hex. Then, beyond there, let's take a look at a bit more of a complicated example. And for this one here, I've decided to use sprintf, and that's just to show you that you can use printf, but printf normally goes to what's known as standard out. And you can see that down here for this in a sec, and I'll get to that in a second. But there's really 3 different main standardized buffers, and we've discussed them earlier when we went over things like cout, cerr, and cin. And basically, these correspond to the same things, just that cout, cerr, cin are the C++ version, and standard out, standard error, and standard in are the C version. And those are pretty common to basically every operating system, and they're predefined buffers in memory that are used for input and output. And for those, printf by default goes to standard out. Or more accurately, printf goes to standard out because it's just a version of fprintf that already has this argument supplied for you, so that you don't actually end up needing it to specify standard out every single time you're going to call fprintf. But sprintf takes in a string that you want to print to. In this case, it's our character buffer here, and you need to be certain that you have enough space in your buffer to fit whatever size string you're putting in there. So if for whatever reason I put this down to 20, all of a sudden sprintf might be overriding memory I should not have access to, and it'll either crash my program or it will cause behavior in my program that should not occur. And sprintf is one of the most common and original problems for how hackers have been able to gain control of systems over the years, is that people won't check their buffers, won't check the lengths of the strings that they're getting in, and as a result, it will wind up causing these sort of errors of all of a sudden you have stuff overin that shouldn't be. However, in this case here, this is just to show you that you can do some of these multiple ones and how you might end up using them in order to, in this case, output today's date in terms of outputting the day, then the month, then the year. And I'm not going to get into exactly how time ends up working in C and its different structures for that. That's really something you can look up on your own if you're interested in it. But as you can see, it's intermixed with just these slashes, which are normal characters. It has multiple ones of these, as well as you can even do operations within here, same as a normal argument to a function. And then it'll output this to this buffer, and I'm printing out this buffer twice. Once to standard out, once to standard error. And the important thing to note is that you can see these two appear here and here. And the odd thing that you'll notice is that this line appears between the two of them. And that line happens to be up, if we head up to here, where this is. And the whole problem for why this is getting output before this is getting output is that there is a function known as flush. And this isn't something I want to get too much into, but what flush does is it is designed to basically take in a buffer or take in a stream, and that's supposed to take that, so in case I put in here C error, what it would then do is it would cause C error to end up being forced to the screen. And the reason why you don't always call flush whenever you end up doing fprintf or printf, and why it doesn't automatically display it, and the reason why this one's first is that up here you'll note that we use endl. And if you look in here, it ends up calling flush. So that happens to be why we end up with this line being output before we wind up with our standard error, even though this operation takes place first. And that's because it's very expensive to print stuff to the screen. In general, input and output are going to be the most expensive parts of pretty much any program or anything that you have to deal with. Even if technically you spend more time on the CPU, that's because of the fact you're getting more stuff done. The time it takes to do stuff on the CPU is very tiny compared to the time it takes to either write something to a screen, write something to a buffer or a hard drive, or send something over the internet. So as a result, you don't want to always be flushing stuff to the monitor whenever you want to print something out, because otherwise it's going to slow down your program drastically. Same thing for in case you're writing a log file. You'll want to basically store that in memory for a bit and then periodically flush that buffer out to your actual file on your hard drive so that you don't end up destroying your performance. And we'll get into different ways of doing that in the future, but it is useful to note, and in this case here you can see how in one case it's output just as normal black text, and in the case of the error output, it ends up outputting it in red text. And these are really the three main ways of outputting information. We'll get into a couple of others in the near future, and the reason why we'll get into those is for when we get into things such as dealing with binary file formats. However, in the next episode, we're going to take a look at how to read in a file. It's going to be very similar to a lot of stuff we've done here, and the reason why we're reading in a file rather than reading in from the console is that when you read from the console, you can end up making certain errors with input, so it just is a bit cleaner for an example in order to deal with it as it comes up with files. As well as we're going to be in the near future reading and writing a bunch of stuff to files, so it makes sense to want to get that practice in now. If you want a bit of time practicing with this, I would recommend just messing around with it until you're comfortable with what the different things do. Create your own printf statements and try outputting different things and seeing how you can end up using the functionality within here to create your own custom tables. If you want to, try creating a custom table of you and your families and some of your friends in terms of just their names, maybe their birthdays, ages, that sort of thing, so as that you can end up trying to output it in a clean manner and get it to appear formatted so as that it ends up looking good. And that is one of the big challenges of outputting any form of table like this, is getting it to look clean and look nice, especially when you're doing it in text. It's a lot easier once we start getting into stuff such as UI. However, that's because a lot of the difficult stuff is being done behind the scenes for you. So thank you very much for watching. Have a wonderful day.